So good morning everyone and welcome to today's lecture in Computational Finance. Yesterday we talked about several test functions that can be used to assess the performance of an optimization algorithm. Actually, you can use those test functions in many applications in numerical analysis, and from those plots you were able to see that some functions do actually look horrible, numerically speaking, but some others seem to be quite harmless at first, but they also pose severe problems to optimization algorithms. For example, this function looks pretty simple and quite easy to optimize, but actually it has numerous local optima. After having talked about test functions, let's now turn to gradient-based methods and more or less the method of steepest descent as one example of a derivative-based optimizer that can be used for unconstrained optimization. Again, remember that this pretty much only works when you have unconstrained optimization, because as soon as you include constraints in your optimization problem, you will probably be forced to look at possible solutions on the edge of the solution space, because in that case, again, I gave you this small example. If, for example, you only want to look at this area here, you can see that the condition and the requirement that the first derivative is 0 is of no use here, because as you can see, the optima lie on the edge of the solution space. And for example, you would have a maximum here and a minimum here, and the first derivative doesn't really help here because it never gets to be 0. Okay. Now we want to look at the method of the steepest descent. It's a gradient-based method, and previously we've seen that we are using an iterative method. That is, we have a solution xk plus 1, and xk is defined to be, for example, we had this on one of the previous slides, is taken to be, here we have it, xk plus 1 is set to be xk, the previous solution, plus a change that is given by a scalar alpha times the direction s, which is also a vector. Okay. Now the question then is, into which direction should we go? If we are at a point or a solution xk, we need to find a solution in which we want to go with a step length alpha. And the method of steepest descent is, well, actually it's what it is, and it's what it sounds to be. It's the method in which you use as a direction for the next solution, you use the gradient. So you take the gradient of f, normalize it by a suitable norm of the gradient. Now remember, the gradient is what? The gradient is the vector of partial derivatives. That is a vector of functions. Now, if you were to insert xk in all these partial derivatives, you get numbers. Actually, no, you get you will get a vector, and then you can calculate the norm of this vector, and you will get a real valued number. So you normalize the gradient by its norm, so it has a length of 1, trivially, and you take as a direction, as a step direction for the next solution, minus gradient, and the gradient is normalized. Okay, now, after having normalized this step direction, this vector, you can choose the step length alpha, and you don't simply choose it to be constant, but you choose it via an optimization scheme, and this one is actually one-dimensional. You try to minimize the following function. You try to minimize f at xk plus alpha times sk just over alpha. You take the previous solution xk and the step direction as a given, and in this case the right hand side is only depending on alpha, and you minimize h of alpha over alpha. and you choose the optimal step length if you have already chosen the step direction as the normalized gradient. Now this is the gradient method, the method of steepest descent. In German it's the Gradientenabstiegsverfahren oder die Gradientenmethode. In German we also say method of steepest descent. And then xk plus 1 is xk minus alpha times gradient, and it's normalized. It converges comparatively slowly and relatively poorly near local optima. The nice thing about this is you only need the gradient. You only need the partial derivatives for this to work. Okay. Now, gradient, any derivative-based method has the disadvantage that, at least in theory, can only be applied to differentiable functions. For a mathematician that might matter, but in many cases, if you know the function is not differentiable, you will simply substitute it with a smooth, continuous, and differentiable approximation. We'll simply choose some points, use a spline or even a polynomial, and just substitute it with a suitable differentiable function. But still, in theory at least, as we are in need of the gradient of the partial derivatives, it should be differentiable. Now, in the vicinity of the desired optimum, you usually observe the convergence speed to deteriorate considerably. And this means that assume, this is a simplification, assume we are looking for this point here. What happens is, for example, we have x1 here, maybe x2 here, then x3, and we are quickly closing in on the optimum, but at some point, the nearer we get to the optimum, suddenly the algorithm jumps between 2 points or near points near the optimum. And this is what is called zigzagging. We'll later on see it on I think I also have it on, I think it comes when in the application in Matlab. You can observe this zigzagging, and convergence speed deteriorates, and this makes the algorithm not too quick. Now, formally, this comparatively poor convergence near the optimum is simply due to the fact that this is a local approximation of the first order. What does this mean? Is everyone aware of Taylor's theorem? In German, Satz von Taylor. Who is not? Okay, everyone, yeah? That's von Taylor? Not really, okay. Who can describe just quickly what Taylor's theorem says?
Is it about the interest rates? Or?
No, that's a different Taylor. What does Taylor's theorem state in calculus? No one? Not even the mathematicians, the math student? Okay. It states that if you have a function and this function has some properties, especially differentiable, you can pick a point on the x-axis and you are interested in what the function looks like. You don't know anything about the function f, but if, for example, it is differentiable, Taylor's theorem states that there exists a vicinity around a certain point A in which you can substitute this function by the Taylor series, the Taylor-Reihe, which is more or less an infinite sum of polynomials. And this Taylor series looks as a very unique definition. It simply is the sum of more or less the function and all its higher derivatives at this point, more or less. And you can see that you need the function itself at this point A, then the first derivative and second derivative, and so on. And you're summing up all these derivatives at this point, and then you have this result that the function itself of which you don't know anything about. It might be a polynomial, might be the exponential function. You have no information about this. You can simply substitute this function near in this vicinity of a point by its Taylor series. And this is quite interesting because the Taylor series is more or less a polynomial. And this is not an approximation, but there is a vicinity near this point, around this point, where this is exactly given. And this is important because it is the foundation for all approximations, more or less. You know? And of course, there are some caveats. First of all, you need the function to be differentiable. And the second caveat is it's not a constructive, how shall I put it? The theorem itself has no immediate practical application because it simply states that there is a vicinity. For example, if you have a point a equal to 5, you simply know that there is an interval around 5 in which the function can be substituted by the Taylor series. It doesn't say it's between 4 and 6. It might also be 4.9, 5.1. You have no information how small this vicinity is, this interval is. You simply know that there is at least one infinitely small, maybe, interval in which you can substitute the function by its Taylor series. And the Taylor series looks. Oh, let me just pull the Taylor series from Wikipedia. It's easier. I don't want to make a mistake. Now this is the Taylor series, and this is how it's defined. It's the infinite sum, starting with 0 to infinity of f at a divided by n factorial times x minus a to the nth. And then you can see it starts with the function itself, then it's its first derivative, second derivative, third derivative, and up to infinity. Now, in many cases, if you have a fourth or fifth derivative, it usually will vanish to 0, but it might not. And what you do is, you know that this Taylor series is equal to the function around this point A. But if you're not willing to calculate all those derivatives, you can simply cut off all the higher derivatives. And this is what we call a first order, second order, third order approximation. If you use just the first derivative and you cut off the Taylor series after n equal to 1, it's the first order approximation. If you cut it off after the second derivative, so after f second derivative at a 2 factorial x minus a to the squared, then it's the second order approximation, and so on. So every time you see a first order approximation, second order approximation, you have to remember that this relates to Taylor's theorem, that you use the Taylor series, you use derivatives, and you simply cut off all the higher order terms here. Okay. So this is why here, actually, if you use the method of steepest descent, and you're only using the first derivative, convergence becomes relatively poor because this is only a first order approximation of the function. Now, in many cases, it makes sense to make an approximation of the second order. And one example for such a procedure is Newton's method. And Newton's method, we've seen this in one dimension, and this is the variant for in the multidimensional case. Theoretically, if you use a first order approximation, you are only using the first derivative and you are neglecting all the information you have on the curvature of the function. Now, if you want to include this information, you can do so, and you use a second order approximation, and in this case, fx plus delta can be approximated by f at x plus the gradient transpose times this vector delta plus 1/2 delta transpose times the Hess matrix times delta. So this is a Taylor approximation of the second order. You're using all the terms up to the second derivatives, in this case the partial derivatives, and you need the Hess matrix. The Hess matrix simply includes all the partial derivatives, second partial derivatives. So 1, 2, 2, 1, 1, 1, and 2, 2 in 2 dimensions. If H now is positive definite, that is symmetrical, and if x times the matrix times x is larger than 0 for all vectors that are not equal to the 0 vector, then f is locally strictly convex, and minimizing the Taylor approximation returns a minimum of f. So this is equivalent to using the Newton-Raphson algorithm on this necessary condition that the gradient has to be the 0 vector. And then this is the Newton method. It looks similar to the method of steepest descent, but it has some additional, some changes to it. As you can see, the k+1 solution is given by the previous solution minus alpha, the step length, times the inverse of the Hess matrix times the gradient. It shares some properties with the Newton-Raphson algorithm in 1 dimension. It's quite fast. It has quadratic and fast convergence, but as you can see, it doesn't mean that the algorithm itself is faster. Why? Convergence is better, but in every iteration you need to evaluate more and you need to do more computations. In the method of steepest descent, you only need the gradient and you only need to put numbers into the gradient and you have to evaluate the partial derivatives. Now here, you need the gradient and you need the Hess matrix, and you have to include and input all the function values of the solutions into the gradient and the Hess matrix. And in this case, quadratic convergence makes the algorithm faster, but because you need more computations in each iteration, this might mean that the algorithm itself is not too much faster than the method of steepest descent. Okay. And of course you need the gradient and the second derivatives. Okay. Now next, I already talked a little bit about derivative-free methods. Derivative-free methods, which are more or less heuristic algorithms, they try to look at a set of possible solutions, and they try to throw out the worst ones and insert new potential solutions, and then you try out all those solutions, and at the end you hopefully get a good solution for your problem. This is the Nelder-Mead algorithm I want to show you. Nelder-Mead is quite simple because it's more or less a very sophisticated way of just pulling up a vector with, say, 10 entries, and you try out new solutions, you throw out the old ones, and you simply try out new ones. And it's more sophisticated than that, but that's the basic idea. There are nowadays, in heuristic optimization, a huge number of even more sophisticated algorithms that pick up ideas from usually biology and engineering. Famous examples include simulated annealing. Simulated annealing is an algorithm that mimics the cooling down, I think, of steel rods inserted into cold water after heating. So if you have a steel rod that has been forged and that is all still melting hot, you cannot simply throw it into cold water because otherwise the steel might crack, might get cracks. And there is the process of annealing, which means that you slowly have to cool down the steel in order for the steel to keep its best properties. And simulated annealing picks up this idea how this annealing is done, and it simulates it. And I have no idea how the algorithm works actually. I still remember what the idea behind it is. Next thing is harmony search. Harmony search is an algorithm, also a heuristic algorithm, that picks up the idea how orchestras find the perfect harmony, because you have many musicians and they need to find the same harmony. And there are also, of course, genetic algorithms that pick up ideas from genetics. You have a population of genes, and some genes are thrown out, others are formed by combining previous genes, and this is how populations work in biology. And there are some algorithms, genetic algorithms, that follow the same idea. Now, Nelder-Mead is quite simple, and you will see how this works. The advantage of all of these algorithms is that they are heuristics, and they usually don't require derivatives. You don't need any information on the function. If it's not differentiable, it's okay. And you don't need the first or second derivatives. The disadvantage is, of course, you have a hard time to prove that the algorithm converges and that it can actually find an optimum. It's a heuristic, and more or less you're just using a shotgun and shooting into the forest. You're just trying out different solutions, and you try to find better ones, but this is a heuristic. Okay. Moreover, it might also be that such an algorithm is quite suitable in case you don't have the function itself. In some applications, you don't know what the function looks like. You only have data. You have simulated data, and you have no clue what the function f looks like. And if it's implicitly given by data, there are two things you can do. You can either use a heuristic, an algorithm like Nelder-Mead, or you can try to approximate the function first, or approximate the data first to get a function. But then again, it's already a first approximation to your data. Okay. Now, this is the Simplex Algorithm by Nelder-Mead. Basic idea is you take n+1 values of the target function, you exclude the worst ones, and replace it with new ones. And the new point is determined by mirroring at the center of gravity of the simplex of the remaining points. So what does it mean? Simplex is another word for a complex polyeder. Simplex, it's also why the simplex algorithm in linear programming is called simplex algorithm. You take the simplex of the remaining points, you calculate the point of gravity, Schwerpunkt, and then you mirror it. And you try to find a point that is exactly across the simplex and across the point of gravity. This is shown here. You have 3 points, x1, x2, and x3. Now it's not a very complex simplex, it's simply a triangle. And you would, for example, see that the point of gravity is here. You see that x3 is, in this case, the worst point, and you would mirror it, and then you would use this point as the next possible solution. Then you have x1, x2, x4, and then you do the same. Then you might realize that this one is the worst case, or the worst solution. Then the point of gravity would be here, and maybe then you would try to mirror it here. It's not really exact, but you should get the idea. Then you have this point, and then you have these 3 points, and so on. And you continue to do so until you are satisfied with your best found solution.
Excuse me?
Yeah?
From what do you know which points are worse than the other?
It's quite simple. If you have 10 solutions, you insert it into the target function, into the objective function. For example, if we want, let's make a quick example. You have f equal to x squared, and you want to minimize it. It's quite simple. The solution is 0. So you would try out 1, 2, 3. You would insert 1, 2, 3. You would find 1, 4, and 9 as target values. And you can see that 1, 4, and 9. So the 9 and correspondingly x equal to 3, that leads to f is 9, is then the worst solution, the worst case.
But isn't here the idea that I do not have a function, I only have the data?
Yeah, but you will, okay, I see you where you are getting at. This here, this means that you have x and the function values. But you don't have, for example, if I gave you 1, 2, 3, and 1, 4, 9, you would have data, but you would have no complete information on the function itself. And you don't have any clue about what happens in the function between 1 and 2 and 2 and 3. And then you have two possibilities. You either do the optimization just based on these 3 points. You can do this. Or you could interpolate or approximate the function by using these 3 points, for example, and putting a polynomial through the points. Yeah? But you always need the function values. If you only have the points x, that doesn't help you. No? Okay. So in this case, for example, you would know that x equal to 3 with f equal to 9 is the worst point, and then you would throw it out. Okay. Now the rest of the algorithm is quite elaborate, and you can see how this very simple idea has been tuned to improve on the performance of this algorithm. And I would say we can simply quickly go through all the different steps. You don't need to memorize this. You will see how the algorithm has been tuned. You start with n+1 values. You have to determine the corresponding function values and sort them by size. So you have f x index 1, f at x index 2, and please remember that this here means the index in brackets. It means that actually this has already been sorted. So this is not the smallest x value, but it is the x value for which we have the smallest function value. No? So x1 is the best solution in the kth step, and xn+1 is the worst solution in the kth step. Then you have to calculate the point x0 as the center of gravity of the remaining points, so of the points xi from 1 to n. That means we exclude this one, and we calculate the point of gravity, which simply in this case is the average. Yeah? So this is x0. Then we calculate the mirrored point. xr is x0 plus alpha times the difference between x0 and xn+1. If xr returns a better function value, replace it and go to step 1 again. If not, if the new point is the best value so far, there's one extra bracket here, calculate the expanded point xe, x0 plus gamma plus times x0 minus xn+1. Replace the worst point either by the extended or reflected point, whichever provides the smaller function value, and go to step 1. At this point, we should have f at x0 is larger or equal than xn, calculate the contracted point, and so on and so on. You calculate new points, you compare the new points with the previous points. If it is better, okay, replace it. If it is not better, don't replace it, calculate another point, go into the other direction. If you see that actually this is the best point so far, take it a step further. This is why we expand the point, x0. And it goes on and goes on. You can see some default values for these parameters, but the basic idea remains the same. You have n+1 values of x, you try them out, you take the worst one, you throw it out, and you try to calculate a possibly better solution. And if you see that you are going into the right direction, go a little bit further. If you see that you are moving away from your best solution, go into the other direction. This is an elder meat. No? And we will shortly see this in Matlab. Okay. Now we want to minimize the following very simple function. F of x1, x2, x1 minus 2 to the fourth plus x1 minus 2 times x2 squared. And obviously you can see the solution is given with 2, 1. If you insert 2 and 1, you can see that the function is 0. And as you only have a squared term and a term that is given to the fourth power, this is strictly non-negative, and then of course f at 2, 1 gives the global optimum. The gradient, the vector of partial derivatives, is also calculated quite simply. We can see that at this point 2, 1, the gradient yields the 0 vector, and we can use both fmin search and fmin unc for minimizing f. Fmin search is a variant of the Nelder-Mead algorithm, so it's a derivative-free algorithm. One has to be, I think, fmin search, it should work. There are some differences between fmin search and fmin unc, but in this case, both should work. Fmin unc is a set of algorithms that are derivative-based, and fmin unc will decide automatically on which algorithm it should use. We can see that later on. Now we start with fmin search. We first define our function with the function handler at, and we can just say x equals fmin search of f, and as a starting vector we use the 0 vector. The result is x equal to almost 2 and almost 1, and the function value here is 2.9 times 10 to the minus 17th power. So it's close to 0, at least it's the best we can do on this computer. But 2 and 1 is a good solution. Okay. Now we do the same with fmin unc. Fmin unc gives out a warning: gradient must be provided for trust region method using line search, optimization terminated, relative infinity norm of gradient less than options, tolerance function, x is 1.98 and 0.99. And you can see that actually it's a very simple, very simple function. You could even see the global optimum with your own eyes. You could be able to calculate this on a sheet of paper simply by taking the gradient and setting the gradient to the 0 vector. And both algorithms that are highly tuned and quite sophisticated give out different results that differ by almost 10 digits. So first of all, we had 10 to the minus 17th, and now we have 10 to the minus 8th power, and this is quite striking. Why? It's quite simple. It depends on how good the approximation of the gradient is. Now, fmin unc gives a more or less slightly worse result than fmin search, and the reason for this is that the target function is actually relatively flat near this point 0, 1. And Matlab, of course, okay, I have to go back one step. Has any one of you ever heard of symbolic computing? Never, okay. No one, not even the math students, okay. Symbolic computing is the area in mathematics, especially in algebra, in which you try to solve equations, not numerically, but symbolically on a computer. And what you do is, what would you do if I gave you, for example, let's see, and something like this. You would immediately see that this is a system of equations, 3 variables, and you would immediately start to try to solve this system of equations on a sheet of paper. And in your head, you would be using symbols. You would use A, B, and C. and you would probably, especially if it's a little bit more complex, you would not expect the computer to be able to do this exactly, analytically, but you would assume that the computer tries to find an approximation and numerical solution to this. Now, computers usually try to find approximate solutions. We've seen this all the time. And if you want the computer to work with symbols and not with numbers, it needs to do symbolic computation and symbolic computing. And Matlab, for example, can do symbolic computing, but you need an additional toolbox. That's an add-on for Matlab and even Octave. It's usually quite difficult. Symbolic computing takes up much more time than numerical analysis because it will yield an exact solution to your system of equations, or to your equation. And here, for example, with a gradient, now what would we do if we wanted to calculate the gradient? We know that there are certain rules for calculating the gradient, and for example, we would say, okay, this is term to the fourth power. Now take the 4, put it in front of the parentheses, and x1 and so on, and we would calculate the derivative symbolically. It would take some time, but in the end, we would get the exact solution for the gradient. Now, what does Matlab do? As long as it does not use the symbolic computing toolbox, Matlab will simply do the following. It will take the function, approximate it with a linear line, look at the tangent line, and use the tangent line as an approximation to the gradient, to the derivative. So it uses a numerical approximation to the gradient and not the exact symbolic solution to this. And as it uses a numerical approximation, this is why the second algorithm, f-min-ang, that is derivative-based, is slightly worse than f-min-search that uses the Nelder-Mead variant. And you can see this from the documentation. By default, f-min-ang chooses the large-scale algorithm if you supply, that's an error in the documentation. If you supply the gradient in fun, this algorithm is subspace trust region method is based on the interior reflective Newton method. But still, f-min-ang with a large-scale option set to off, with optim set uses the BFGS quasar and Newton method with a cubic line search procedure. They both use a numerical approximation to the gradient. Does everyone see the difference? If I use this gradient, I have the exact gradient, the exact derivative. But if I take this function, and the function looks like this, and I simply say, okay, the derivative is this line, this is an approximation. And I already get one error that is included in the very starting parameter for my optimization. Now, I can improve on this a little bit. How? I can use the analytical gradient. If I know this, if I've computed it symbolically, either on a computer or on a sheet of paper, I can do the following. Grad f is now defined as the gradient, and I set the options. I put here an on, this one is for the gradient, I think, and then x equals f-min-ang, f and grad f. So I supply the function with the gradient, with the analytical exact gradient, and suddenly I am improving my final solution, my result, by almost 8 digits. So this is a huge improvement on the error when it comes to this derivative-based optimization algorithm. And the reason for this is exemplified in the next example. Now, what do I do now? I always have this tech error here. This one, this is just a this is supposed to be a red 6. The text color is not a Matlab code, it's LaTeX. Now, I use grad f1, and what I do is I switch one number in this gradient. If you compare it with the solution here, you can see that this is 4 times x1 minus 2. And here, it's 6 times x1 minus 2. So I miscalculated the gradient. This one is not the exact analytical gradient, but there's a slight error in the first coefficient. Now see what happens. Maximum discrepancy between derivatives 16. Warning, derivatives do not match within tolerance. Derivative from finite difference calculation, user supplied derivative, difference minus 16. And then strike any key to continue. Optimization terminated, 1.9841. And let us see. It's even slightly worse than the previous solution. So what happens now? Matlab is supplied with the analytical gradient. It compares the analytical gradient with its own numerical approximation. It sees that the provided analytical gradient doesn't match its own numerical approximation within tolerance bounds. And then it tells the user, look, you've given me the wrong gradient. Do you want to continue? Yes. And we continue, and it uses a different algorithm, but still the result is even slightly worse than before. Yeah.
How good does the supplied gradient have to be? If I just put in x, does it...
One would probably have to look at the maximum discrepancy between derivatives. One would have to look up the tolerance bounds, but I think you can also insert them in the options. I think so, yeah. Here, I think this tol_fun option, one would have to look this up in the documentation, and there you would see what the tolerance bounds are for this comparison between the analytical and the numerical gradient. Again, these are very simple examples. I mean, this is a function in 2 dimensions, very low dimensional, and you could immediately see the best result, the exact result, by simply looking at the function. But still, the computer has a hard time finding this optimum here, and it's not close to being exact. Okay. So this is unconstrained optimization in Matlab. You can use fmin search, you can use fmin unc. One which should keep in mind that even with a very simple example of such a function, Matlab will give different results with different algorithms, and one would have to see which algorithm fits the situation best. Okay. Now, let's now turn to optimization that is constrained, that is with constraints. We try to minimize f, given as a function of a vector again, subject to hi of x is equal to 0 and gi of x is less than or equal than 0. Now, this is important. Usually, all those algorithms and all those documentations are standardized in such a way that you don't have equations and inequal equations like this, for example, 3x1 plus 3x2 is smaller than 5, but you always standardize it in such a way that you have 0 on the right-hand side. So this makes it quite simple, and they should always be given in equation form or less than or equal than 0 form. Now, again, remember the stationarity of the function is no longer necessary. It's no longer a necessary condition for a point to be an optimum. Why? Again, if you have a function like this and you only look at this area here, the function's derivative will never be 0 in this solution space. And you cannot simply solve for the first derivative to be 0 or the gradient to be 0, but you need to look at the edge as well. Now, you can solve this problem by so-called penalty function approach. Another procedure is to derive different optimality conditions. The first one is very simple, and you will immediately understand what is meant with a penalty function approach. The second one, the Kkt conditions. This is, I would say, probably the hardest part of the lecture. The Kkt conditions, you've probably seen this already. In the one-dimensional case, in the special case of a one-dimensional function, do you know what the Kkt conditions actually are? It's the Lagrange approach. It's Lagrange or optimization. Yeah? You might remember this, that you have Lagrange multipliers, you have a function with several constraints, and you simply insert all the constraints in equality form, in equation form, that are equal to 0 with a Lagrange multiplier in the objective function, and then you optimize this and you have to calculate all the different partial derivatives. And this is a special case of the Kkt conditions, and this is more general. The penalty function approach is actually even more simple. What you do is, if, for example, you want to minimize f, I missed this one, subject to hi equal to 0, you can transform this into one simple function. You now define a function phi of x and sigma that is defined as f of x plus sigma times hi squared at the vector x. Now, what does this mean? Why is phi defined in such a way? Now, the function h has to be 0 at the solution x. Any deviation from f from 0, of h from 0, any deviation is either positive or negative, but both are bad. If you square them, you will get the squared error. And you want to minimize f, and now you punish f for violating any of the constraints h by simply adding the squared error term to the function. And this parameter sigma governs how bad the punishment is. If sigma is equal to 1, it's a moderate punishment. If sigma is 100, you're bashing, really bashing on f for violating any one of those constraints. And this is why it's called a penalty function approach. You simply punish your maximization, your minimization scheme by adding the squared errors times sigma to the function. Now this is more or less a heuristic approach. You simply boil down your optimization under constraints to an unconstrained optimization of an objective function that looks slightly different. Yeah? Now, if the solution lies on the edge of the permissible solution space, then with an exterior penalty function approach, the optimal, this is a bad translation, the optimal solution is only achieved within the limit value. And if this is undesirable, the use of an interior penalty function approach may be recommended. And we will later on see how this works. Or actually, you can already imagine what an interior and an exterior penalty approach is. The first one, an exterior penalty approach, is what? You start somewhere at a point that is not permissible, and you can see that your function is punished very strongly. And then you move into the direction of the permissible space, and you move into the direction of the solutions at which the constraints are fulfilled. So you're reducing the punishment. An interior penalty function approach simply starts in the middle, and it sees that the function fulfills all the constraints, and the solution fulfills all the constraints, and then you try to move into the direction of the edge, and you try to find a solution that still is permissible. Now, at this, a suitable threshold function, a barrier function is introduced which strives towards infinity if x from within the admissible solution space strives towards its edge. One example of this is this function b. It's defined as minus the sum of 1 over gi of the let me just see. No, okay, I pushed one too hard. Yeah, let me just go back one step. Here you can still see how you can transform constraints with inequalities. The same thing, you know that, for example, if you have constraints in inequation form as inequalities, you can just take the positive or the negative part, and then you would only punish the function for violating, for example, the numbers to be positive or negative. Yeah, you can also do the same here. You can still square it. And all these three approaches describe so-called exterior penalty function approaches. Yeah? So they are approximating the solution from outside of the permissible set of solutions. Okay. Now, this is one example, and the G is, as you may remember, from the constraints in inequation form. And then you try to minimize f plus sigma times this function b for decreasing values of sigma. Yeah? And this is also something you will try. You will not use a constant sigma, but you will try to increase or decrease sigma depending on your strategy you're following, whether it's an interior or an exterior penalty approach. Why? Because you might start with a solution at which all the constraints are fulfilled. Then you move into the direction where some constraints are not fulfilled, but still the solution is better than the previous solution. But this is not okay. I mean, the penalty function approach is an idea to find a solution, but at the end, all constraints have to be fulfilled. Yeah? Think of an economic example. If you, for example, you have a production program and you want to maximize or you want to minimize costs, and you have a budget constraint, this budget constraint is absolutely binding. You cannot say, okay, the budget constraint is slightly violated because my optimization is a penalty function approach, but in the end, all constraints have to be fulfilled. So what you do is, you increase, for example, sigma, and you signal to the algorithm, okay, you're still violating some of the constraints by a little bit, but you need to move away from this. Yeah? And then you increase sigma, you punish it with a higher sigma, and the algorithm is supposed to move away from this violation of the inequations and of the constraints. Now, if the expression sigma times b, if this penalty term is small enough, or in best case, close to 0, the algorithm is aborted. Now let's look at a small example. Fx is given by x minus 1.5 squared, and y minus 0.5 squared, such that x and y are smaller than 1. Again, optional. I don't know what my translation program did here. The optimal solution is given by 1 and 0.5. And an interior penalty approach could, for example, be x minus 1.5 squared plus y minus 0.5 squared plus sigma over 1 minus x plus sigma over 1 minus y. You can see that this is here, that this is a penalty function approach. If you violate the constraints, your function will be punished for this, and we can visualize this in Matlab in the following. We define f, which is here given by sigma, y, and x, and then we use a mesh grid between 1 and 0, and you can see different subplots, and you can see that sigma here decreases. And remember, the optimal point is given at 1 and 0.5. So here is our optimum. And you can see, well, what can you actually see? These are contour plots. So there is x1 or x and y on the x and y axis, and those contour plots show you by means of colored lines and colored curves what f looks like. And for example, here you can see that with these red lines, the function takes very high values. Here, the blue lines show you that the function is quite low or small here. Now, what do these contour plots for different signals tell you? What do they show you? Any idea? Now, in the upper left plot, you can see that actually sigma is so high, the violation of those constraints is not punished at all. Yeah? The function is just very low for all those points, and there is not a large penalty term that is added to f. Now, by slowly increasing sigma, you can see that suddenly the function that used to be quite low suddenly is turned up, because at the borders where the constraints are violated, you now have large error terms being added to f. And on the lower right plot, you can see that actually here, at those points, you have a function at which you can see it's now more difficult to find a solution that fulfills the constraints. Okay. Now, this penalty function approach is comparatively simple. However, with exterior penalty functions for large values of sigma, you might get some numerical problems. The approaches with penalty functions should therefore be used only as a starting point for more sophisticated procedures. As you can imagine, this is a very small example with 1 or 2 constraints and a very simple function. As soon as you have a more complex situation, if you have more constraints, simply adding all those constraints in your penalty function will yield a function that is just that long. And the optimization of this function will become extremely hard. So this can only be a very first crude approximation, and we will have to look at the Kkt, the Karush-Kuhn-Tucker conditions. Okay. Now, let's turn to there is actually, I think it's the other way around, Karush. Let's turn to the Karush-Kuhn-Tucker conditions. We start with an optimization problem that is still given by the minimization of f subject to h equal to 0 and g equal or less than 0. Now the stationarity of f is not relevant, but the stationarity of the so-called generalized Lagrange function. Now, the generalized Lagrange function is given by f plus the sum of lambda I times hi plus the sum of mu I times gi. And this is the generalized Lagrange function. As you can see, we now include all the constraints with the different sets of Lagrange multipliers. Okay, so this is the starting point. And again, I'm pretty sure it's Karush-Kuhn-Tucker. The Kkt conditions state the following. Now assuming we're given function f, hi, gi, and all are continuously differentiable and x star is a valid solution and fulfills certain regularity conditions. We'll talk about these regularity conditions later on, these additional conditions and requirements. Then a necessary condition for the existence of a local optimum in x star is the existence of numbers lambda I star and mu I star, so that the following holds. Gradient at x star plus sum of the Lagrange multipliers times the gradient of the constraints in equation form plus the sum of the Lagrange multipliers times the gradient of the constraints in inequation form has to equal the 0 vector. And mu I star times gi at x star has to be equal to 0. In other words, this is a generalization of what you already know. In the special case of a one-dimensional function with constraints in equation form, you simply put up the Lagrange function, and the Lagrange function will look like fx plus lambda times la 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 la, and then you calculate the two partial derivatives, and you have to set it to 0, and then you solve for lambda and x. So this is the special case you've seen in the math introduction. This is the generalization. And these are the Karush-Kuhn-Tucker conditions, which means that the sum of all the gradients of all this generalized Lagrange function has to be equal to the 0 vector. Now, a couple of things are important. First of all, f, hi, and gi have to be continuously differentiable. What does it mean? Does everyone know what continuously differentiable means? It means the function is differentiable and the derivative is continuous. Stetig differenzierbar. Okay. Second, the solution needs to fulfill certain regularity conditions, and this is where it gets tricky. I will show you some of the regularity conditions later on, but it's not so simple as in the one-dimensional case with just constraints in equation form. If you have this very general setting with inequations, equations, a multidimensional function, you have to make sure that actually this Karush-Kuhn-Tucker conditions apply, and this is where you need these extra requirements. Okay. Now, in case without constraints in inequation form, we have the classical Lagrange optimization with constraints in equation form. Those parameters lambda I and also mu I, they are called Lagrange multipliers, also sometimes referred to as dual variables. If the function f and the constraint conditions gi are convex and the functions hi are affine linear, the Kkt conditions are necessary and sufficient for the existence of a global optimum. Again, we see that if some convexity is given, then a local optimum suddenly becomes the global optimum. As I mentioned, you need those regularity conditions. And this is the difference to the special case above. You cannot simply calculate the gradients and apply the Kurt-Kontaker conditions, you have to make sure that this theorem applies, that this theorem holds. So some regularity conditions are given here. For example, the linear independence constraint qualification. This is even a special abbreviation for it, LICQ or MFCQ. Mangasarian-Fromowitz constraint qualification. You can imagine that this has taken some efforts by mathematicians to come up with these conditions and qualifications. For example, the gradients of active constraints in inequation form and gradients of constraints in equation form are linear independent in point x star. Okay. Gradients of active constraints in inequation form and gradients of constraints in inequation form are independent in point x and positive linear and so on. And you also see that the second one follows from the third one. You don't need to care about this. You simply need to remember that you cannot simply use the Kurt-Kontaker conditions and be done with it, but in contrast to the special case in one dimension and constraints in equation form, you first have to make sure that this theorem holds. And you can do this by checking these conditions. Okay. Now, the Lagrange multipliers were already referred to as dual variables. And it's interesting to turn to Primal-Dual Theory at this point. I guess I remember from yesterday that none of you has ever seen the Simplex Algorithm. And you have? Okay. So what is the funny thing about the Primal-Dual Theory in linear programming? Okay. I don't remember the specifics, but I still remember that actually if you have a linear program, for example, very simple example, you want to maximize production. You want to maximize production, you have some resources, you have a budget constraint, you have a machine constraint, for example, you can use only these and these machine hours, and you have a linear program. Then you can try to use the Simplex algorithm to maximize production. But you can also switch it equivalently to a minimization problem, which is the dual problem. Yeah? The maximization is then the primal, this Primal-Problem, and you can switch it to a minimization problem that is equivalent. And the solution to the primal also gives the solution to the dual. Do you know what the dual then is? If you want to maximize production, the minimization does what? In simple terms, you try to minimize the remaining resources. You can either maximize production with a given resource, or you can equivalently try to minimize the remainders of your constraints. And this is how it works in Primal-Dual Theory in linear programming, and this is the same here, just it's not restricted to linear programming. Now, first of all, we illustrate the Kkt conditions. We want to maximize. You can see this is already a very simple example from production theory. You have a production function xi to the alpha power times x2 to the 1 minus alpha power, which simply is what? It's a Cobb-Douglas production function, exactly. And we have a budget constraint, P1 times x1 plus P2 times x2 has to equal W. So this is our budget constraint. The Lagrange function is given by f plus lambda times the constraint equal to 0. The three Kkt conditions are then given by partial derivative with respect to x1, x2, and lambda have to equal 0, and solving this system of equations yields this solution, x1 star and x2 star. Okay, quite simple. Now, if the gradients of the constraint conditions in point x star are not linear independent, they may not be used as a base for the representation of the gradient, and in this case, the stationarity property is also not fulfilled and a local minimum is not recognized. I can illustrate this in the following. We now want to maximize x1 plus x2 with two constraints, x2 minus x1 to the third equal to 0 and x2 equal to 0. This is a trivial example. You can already see that x2 has to equal 0. Then insert x2 in the first constraint. If x2 is 0, then x minus x1 to the third also has to be 0. So trivially, the only allowed, permissible, and also thus possible optimal point is 0, 0. Okay. Now, let's play stupid and let's use the Kkt conditions. Lagrange function, derivatives set to equal, and what can we see? Again, x2 has to equal 0, 1 plus lambda 1 plus lambda 2 has to equal 0, and 1 minus 3 lambda 1 x1 squared has to equal 0. Now, these three Kkt conditions cannot be solved, since the first equation results in x1 is not equal to 0, and this is not compatible with the other two. So in this case, we can actually see very simple function, very simple constraints, but Kkt doesn't have it. And why is this? It's simply due to the fact that the gradients of the two constraints are parallel. They are parallel to each other, and they cannot form a base of the R2. Now, you can see this. First one at 0, 0 is just 1, 0, and the second one is the same, 1, 0. So you have two vectors, they are identical, and then they don't span the two-dimensional real space. So this is one necessary condition you need. Okay. So they do not form a basis of the R2 with which a gradient f can be represented, and we would need two vectors, a and b, so that a times lambda plus b times gamma have to equal 1, 1, and with 1, 0 and 1, 0, this doesn't work. Okay. Now, if you have already seen this in linear programming, you might remember the condition of complementary slack or complementary slackness. In German, it's die Bedingung des komplementären Schlupfes. Very nice name. This refers to the fact that if a constraint condition is inactive in the optimum, the associated Lagrange multiplier must be equal to 0. And if you have already seen this in linear programming, you might know that the Lagrange multipliers actually show you whether you can, you still have some leverage in your constraint, or if it's an active constraint. If the Lagrange multiplier is 0, this means that you can still use some of the leeway you have in this constraint, and you might be able to reduce it. In case the Lagrange multiplier is 0, the constraint is active. And this means that you have used all up, for example, all resources you have in your constraint. Conversely, the constraint belonging to a multiplier that is positive in the optimum must be active. So the inequality is reduced to an equation. For a constraint condition, hi equal to w, the Lagrange multipliers lambda I and mu I describe the sensitivity of the optimal function value to the change in the value w. That is df star over dw. And you probably know this from Lagrange optimization. The Lagrange multipliers tell you how sensitive the optimal function value is to a change in the constraint. If you were to have another resource, another unit of machine hour, another euro in your budget, you know by how much you could increase or decrease, if you want to minimize the function, how you can change the value of your objective function. And these sensitivities are given by the Lagrange multipliers. Okay. Now, we are given a quadratic optimization problem of the following type. Half of x times h times x plus f times x, such that a times x is less than b, and a times x, different matrix A, is equal to B, and x is between a lower and an upper bound. Now, let's look at an example of such a quadratic optimization. We use the unit matrix. Yeah? So this is just 2 times 1, 0, 0, 1. F, A equality, or equation, B equation, lower bound options, and then we do an optimization, and quadratic optimization is done by quadproc, quadratic programming. This is the program and the function in Matlab that does quadratic programming. And then you can see that the solution is 1 and 0. And then you get the lambdas for your constraints in equation form and for the lower bound. And here, for example, lambda for the linear equation is -2, and the lambda for the lower bound is 0, 4. And these lambdas tell you how sensitive your function value is to changes to the constraints, the changes in equation form and the lower bound. And you can change that a little bit, and then you can see how the objective function changes. Okay, Lagrange multipliers. Now, finally, let's turn to duality theory. We want to minimize f still with constraints gi less or equal than 0. Now, this is what we call the primal problem, this primal problem. We don't require anything about s or f, differentiability, something else, and we dualize the constraints and we get the Lagrange function f plus the sum Lagrange multipliers times the constraints. And for a given vector, mu of multipliers, the minimization of the Lagrange function with respect to the vector s is called the relaxed problem. In German, the same word, das relaxierte Problem. What does this mean? It means that we don't look for the best x and mu at the same time, but simply we take a given vector of Lagrange multipliers and we minimize the Lagrange function with respect to just the vector. This is a much simpler optimization, but remember, the Lagrange multipliers might not be optimal. So we are given a Lagrange multiplier vector, and then we minimize L, and this gives the relaxed problem. The solution of the relaxed problem defines the dual function, which in this case means if we take a Lagrange multiplier vector, mu, then the function value of the dual function gives the optimal vector x with which the Lagrange function, together with this mu, is minimal. Now, please understand the difference between the optimization of the Lagrange function with Karush-Kuhn-Tucker and the dual function. With Karush-Kuhn-Tucker and simple Lagrange optimization, we try to find the best x1, x2, x3, and lambda, or mu, in one step. Here, we are simply giving, and we're simply picking one Lagrange multiplier, we set it constant and we leave it, and then we try to find the best set of x variables with which the Lagrange function, together with this mu, is minimum. Now, this is much simpler than maximizing or minimizing the Lagrange function. And then we can look at the dual problem. Again, if we are given the dual function, of course, we can do it stepwise. We can first look for the best mu so that the dual function is optimal. And this is the dual problem. We maximize W, the dual function, over mu. So this is what? We maximize the minimum of the Lagrange function, and we try to find the best x vector, and then we try to find the best set of Lagrange multipliers. So we split it in half. And not surprisingly, it's equivalent under certain conditions. First theorem holds it's weak duality for a vector mu larger than the or non-negative mu. The dual function is a lower bound for the optimum of the primal. So this means that W is less or equal than f at x star for all vectors of Lagrange multipliers. Now this doesn't sound much, but you know that if you take the dual function, and you can see that the dual function is actually quite simple. You simply take one vector of Lagrange multipliers and you do a much simpler optimization. And then you know what your best result can in any case be. The dual function gives a lower bound and we want to minimize. So if, for example, this is the dual function and this is the lower bound and we want to minimize the Lagrange function, we know that actually we can only get as good as this lower bound. So the first result, weak duality, it gives a lower bound for our optimum. And in a much simpler way. And contrary to weak duality in special cases, for example, for a convex target function, in some cases, strong duality applies. In fact, in this case, it is not a lower bound, but we can see that the solution of the dual problem is equal to the solution of the primal problem. So we have the optimum. And this theorem now gives some ideas on this. If there exists a pair x star, mu star with the property x is permissible and mu star is non-negative, and f at x star plus mu star times the transpose times the inequation constraints is the minimum of fx plus and so on, and so on, and so on, then x star is a global optimum of the corresponding primal problem. So in this case, we can see that strong duality applies. But then, of course, this is more the same. To put it in words, and I think the verbal description is much more intuitive, the optimal solution to the relaxed problem is a global optimum of the primal problem provided this pair x star, mu star is primal allowable and permissible, is dual admissible, and meets the condition of complementary slackness. This is here the condition of complementary slackness here. And then the following theorems hold. First of all, the dual function is always concave. So you don't have convexity, but you have concavity. Next, we need the so-called subgradient. Let f be an n-dimensional real function. The subdifferential from f in point x bar is given by, we call this the subdifferential. This is just fx minus f at x bar is larger or equal than g transposed at x minus x bar for all x. And those elements, they are called the subgradients. It's a slightly different definition of a derivative, and because it's not the derivative and it's not the gradient, it's called the subdifferential and the subgradient. Now, what can we do? Let x hat be an optimal solution to the relaxed problem for a multiplier vector mu hat, then g at x hat is a subgradient of the dual function, and consequently the dual problem can be solved by means of the subgradient method according to the iteration. And this is the most important part here. Actually, you can switch the primal into the dual problem, and under rather weak conditions, you can see that you can again use an iteration, an iterative method. In this case, it's not reliant on the gradient, but on a slight variation, the subgradient. But you can see that this is very similar to what we've seen before. This is just the next solution, mu, is given by the maximum of either the zero vector or the previous solution to mu plus alpha times this subgradient. Okay. And this is why actually in linear programming, this is quite simple. In the special case of linear programming, in which case you know that the optimization problem is convex, you always have strong duality. And this is why it is quite difficult and a little bit more elaborate in the general case, but in linear programming it's quite simple. You can switch around from primal to dual, and you can do it with a simplex algorithm and a tableau on a sheet of paper, and you can see that it gives the same result. The dual and the primal are equivalent, and if you solve one, you've solved the other one. No? But this is only due to the fact that strong duality applies here due to the convexity of the problem. In other cases, you might be able to find a solution to your primal by maximizing the dual function via an iterative method. Okay. Yeah. So this is duality and primal-dual theory. This, again, is highly relevant in linear programming, and you use it a lot with the simplex algorithm. In case you have a function that is not linear, you sometimes do have to resort to Karush-Kuhn-Tucker. You have to check for the regularity conditions, and then usually all this is implemented in Matlab or in any other Mathematica or Octave, and you can use it on a computer. It's, however, interesting and insightful to remember that, for example, Matlab also gives you the Lagrange multipliers. And the Lagrange multipliers tell you a lot about the sensitivity of your optimum to changes in your constraints. And you have to remember that even in this more general case, you still have Lagrange multipliers, and they work more or less the same way as they do in the special case with constraints in equation form. They give you the sensitivities of your objective function to relaxations of the constraints, and if you are able to relax the constraints, simply look at the Lagrange multipliers and you know which constraints you have to change and which you can leave because they are inactive. And if you are in need of another method, you can resort to an iteration method, an iterative method that works on the dual function. Okay. Now, on the next slides, you can see some simple examples how linear programming fmin-con, that is function minimization constraint, the standard functions in Matlab work, and then after that, we'll resort to portfolio optimization in practice. I still have to work on those slides, but I would say we stop here. And do you have any questions? Anything left unclear? I guess pretty much stuff to swallow. And then I would just say that we stop here and continue with optimization, Matlab, and portfolio optimization next week. Okay, thank you.